This video introduces a causal mediation estimand known as controlled direct effects. Our goals in this video are to first define controlled direct effects, to connect these estimands to causal estimands that involve longitudinal treatments that unfold over time, and to build intuition for an estimator that's called sequential G estimation. Often in causal inference, we begin by looking at total effects. The total effect is something like the average value of an outcome that would be realized if a treatment variable A were hypothetically set to the value of treated versus if that treatment were set to the hypothetical value untreated. Mediation estimands take average causal effects and investigate the causal process by which the treatment affects the outcome. We often talk about how a treatment A might affect the value of a mediator variable M, which in turn affects the value of an outcome Y. We might also think that the treatment has direct effects on that outcome that don't flow through the mediator. Mediation is all about studying these direct effects and these indirect effects. When thinking about mediation questions, we first think a lot about pretreatment confounders. Now, pretreatment confounders, X in this graph, they're variables that affect the value of the treatment A and the outcome Y, and possibly the mediator M. These confounders are exactly as they are in standard methods for causal inference with total effects. With mediation, we also have to think about a second set of confounders. These are called intermediate confounders. An intermediate confounder is a variable that is a cause of the treatment. Here, the treatment A affects the value of Z, which affects the value of Y. One way that the treatment affects the outcome is by changing the value of the intermediate confounder. But the intermediate confounder is a confounder of the effect of the mediator on the outcome. So here we're interested in how the value of the mediator M affects the outcome Y. And when looking at that causal effect, we might need to adjust for this intermediate confounder Z. Intermediate confounders are challenging because they are both part of the causal process by which the treatment affects the outcome, and they are confounders of the causal process in which the mediator affects the outcome. And we thus have to handle them carefully. So before defining controlled direct effects, I'm going to use a new tool that we haven't yet learned. This tool is single world intervention graphs. SWIGs are a generalization of DAGs to the setting where on the right side of the graph, instead of having an outcome Y, we have a potential outcome like Y superscript A. So you'll recall that a DAG is just a graph that shows a set of variables represented as nodes connected by edges that have directed arrows pointing for which direction causal effects flow. Here we have a treatment A that affects an outcome Y, and a confounder L that affects the value of both the treatment A and the outcome Y. In a SWIG, we might look particularly at the potential outcome that would be realized if the treatment were set to the value little a. We denote this on the right because instead of having just Y, we have Y superscript little a. On the left side of this graph, we see we have our realized treatment variable, capital A. It's affected by the confounder L. But then we're going to imagine a hypothetical world in which that treatment is set by some intervention to the value little a. Now, in that hypothetical world, you'll notice the value little a is not a consequence of the confounder L because it's set by an intervention. You'll also see that all variables downstream of little a, they're all going to have these superscripts A because they're all potential outcomes that would be realized in this hypothetical world. So why move from DAGs to SWIGs? We might do this where here our vertical bar denotes the intervention and we have our potential outcome. We might move from DAGs to SWIGs for two reasons. So I think these are especially helpful first in settings where our causal assumptions differ for each potential outcome, and second, in settings where we want to focus on the outcome of a particular intervention that we'd like to highlight in our graph. So this first setting, when causal assumptions differ for each potential outcome, let's suppose there's an unobserved variable U that affects the treatment A. I'm going to visualize this in a SWIG here, where I have the treatment A, and I'm going to think a little bit about the potential outcome Y1. This is the outcome that's realized when you intervene to set the treatment variable A to the value 1. Let's suppose this unobserved confounder U affects the value of Y1, so my potential outcome under treatment is some function of this variable U. Let's suppose that U does not affect the value of my outcome under control. In this case, we might be able to identify something about my average potential outcome under control, even when my outcome under treatment is confounded. So In short, the expected value of the outcome under treatment here is not identified because, after all, it is related to the treatment by this backdoor path through U. But the population mean of y0, it is identified here because here the only backdoor path between A and y0 flows through L, and L is a measured confounder that we're able to adjust for. So this means in this particular setting, the average treatment effect on the control, or the units that didn't receive the treatment, it's not identified. But the average treatment effect on the treated is identified because for them, the potential outcome under treatment, which is the hard one to learn about, is just observed directly. This is one setting where SWIGs can help us achieve causal identification when identification would have seemed impossible under a DAG. The second setting where SWIGs can be helpful is when we want to focus on a particular intervention. So let's go back to our mediation setting from the last couple slides. Let's suppose we're interested in the outcomes that would be realized if we intervene to set the treatment to the value little a. So you'll see I've denoted this intervention here. We have the factual treatment variable, a vertical bar, and then the realized treatment value. That treatment value affects the intermediate confounder, which is now a potential confounder, Z superscript A. It affects the mediator, which is now a potential mediator, M superscript A, and it affects the outcome, which is now a potential outcome, Y superscript A. Now we might further be interested in how the outcome would be realized if we intervene to set the treatment to the value little a, as well as setting the mediator to the value little m. So here we're imagining a world where we've intervened and said X affected the value of a treatment, but we're going to think we can intervene and reset that to the hypothetical value little a. Then whatever happens in the world that produces some mediator value, we're going to imagine an intervention that sets that mediator to the particular value little m. And we're now interested in the potential outcome defined over two hypothetical treatment values, the value of the treatment, little a, and the value of the mediator, little m. So I like SWIGs because, especially in pedagogical terms, they're helpful for thinking about why potential outcomes for mediation estimands involve both the value to which the treatment is set and also the value to which the mediator is set. Okay, so let's think a little bit about controlled direct effects. The definition of a controlled direct effect here, I'm going to denote this as tau of m. So the controlled direct effect is defined for the particular value of the mediator, little m. It's the expected value of the difference in two potential outcomes. The first is the potential outcome if you are assigned to be treated, so your treatment is a equals 1, and your mediator is set by intervention to the value little m, minus the potential outcome if you're set to the untreated condition, and we also intervene to keep your mediator at the value little m. So why are controlled direct effects useful? They're useful because they might tell us something about the degree to which the treatment affects the outcome in a world where we block this path from the treatment to the mediator to the outcome by an intervention. We're thinking about a world where A cannot affect Y through the mediator because no matter what happens to you, we're going to set your mediator to the value little m. Thus, controlled direct effects are also all about studying the direct effect of the treatment A on the outcome Y. Now note this direct effect includes what's denoted in blue at the bottom here, and it also includes the effect of A that flows through intermediate confounders such as Z. So let's think about a CDE in a very concrete example. So let's suppose that you are an elementary school principal. You want kids to read books. This is going to be our outcome, is the degree to which the kids are reading books. You have a hypothetical treatment that you think may be helpful. If you send the school librarian to visit a class, that might affect how much kids read books. You might think that this effect operates indirectly. If you send the school librarian to visit the class, the librarian will really play up the school library and convince the kids that the school library is a great place to spend time. Thus, them visiting the class might increase the chance that kids visit the library. And when kids visit the library more, this may also cause them to read books. Second, there may be a direct effect. It might be that when the librarian visits your class, that causes you as a child to become really excited about reading books. And you may then go read more books that you already have in your house at home, or you might visit the public library. Thus, the librarian visiting your class may affect the degree to which kids read books through pathways separate from whether the child visits the school library. If we wanted to think about experiments to study these causal effects, we could think about an experiment for the total effect and then experiments for the direct effect. So for the total effect, you as the principal could assign the librarian to visit random classes. Then you could measure the outcome. At what rate did kids read books in the classes where the librarian was randomly assigned to visit? And at what rate did they read books in classes where the librarian was randomly assigned to not visit? Now, how about the direct effect? We might ask about two direct effects. The first direct effect on the left is the effect of sending the librarian to visit the class in a world where you prevent the kids from visiting the library. This would tell us about the degree to which the librarian visiting the class affects kids reading books through a pathway other than kids visiting the library. So in both of these settings, we might send the librarian to visit random classes. Then we could adopt two different interventions on the mediator. So in the left one that I just described, you close the school library. By an intervention, you prevent any kids from visiting the library. Now on the right, we're interested in a different direct effect. What happens if you send the librarian to visit the class, but you somehow make every kid visit the library? Well, we can imagine that in a hypothetical intervention too. You could hypothetically imagine as the principal that you randomize sending the librarian to classes, but then for all the kids, you make them all visit the school library. In either case, you then could measure the outcome. Now, when you look at these two experiments, you can see that they're different. It might be the case that on the left, the librarian visiting your class increases the likelihood that a kid reads books, even though you've closed the school library. That may happen even if on the right, sending the librarian to visit random classes would not affect whether kids read books in a world where you make every kid visit the library, or vice versa. These are two different direct effects. Because there might be interactions between the treatment and the mediator, the direct effect when the mediator is set to the value 0 is different than the direct effect when the mediator is set to the value 1. The second thing I'd like to highlight on this page is that we are not talking about the difference in kids reading books as a function of librarian visiting the class when we control statistically for whether the kids visit the library. Instead, we're thinking about a hypothetical intervention on this mediator. This is a two-step experiment where you first randomize the treatment variable A, and then you randomize the mediator variable M. Or in this case, you fix it to the value 0 for all the kids in the left case, or to 1 for all the kids in the right case. Okay, so I've already said these two estimands are not the same. There are actually two direct effects, and there are as many direct effects as there are unique values of the mediator. When people talk about the mediation estimand, they are confused that there's actually lots and lots of mediation estimands out there that you can study. Okay, so I just gave a warning that I'm now going to give on the slide to really emphasize it. It gets hard when you have mediators that are not manipulated. So it's hard to study mediators that occur inside a person's head. On the previous slide, our mediator was whether a child visits the school library. We can manipulate that by closing the school library. But often in social science, people try to study mediators that you can't manipulate so easily. So for example, in psychology, you might give someone a psychological stimulus, and that might be randomized. And then you might look at its effect on test performance and the degree to which that causal effect is mediated through stress. You might have a study where you expose people randomly to a racial outgroup, and you look at the effect on voting, and then you ask the degree to which that causal effect operates through racial resentment. You might do a sociology study where you look at the effect of a father being incarcerated on child behavior, and you ask the degree to which that effect is mediated through mother's depression. In all of these cases, no experiment could manipulate these mediators. Mediation is a question that involves the effect of the treatment in a world where the mediator is hypothetically set by an intervention to a particular value. The questions above require us to think about setting stress to a particular value, racial resentment to a particular value, and mother's depression to a particular value. These are all difficult interventions to imagine because these are mediators that occur inside a person's head. As a general bit of advice, it's often going to be helpful for causal mediation if the mediator that you choose to study is something that happens outside the person's head in the world, so we can at least think about what it might mean to intervene and change the value of that mediator. Okay, so an example there is requiring every kid to visit the school library would be a mediator on which it's possible to intervene. Okay, so a second word of warning is that in mediation, we have to think a lot about the causal effect of the treatment and the causal effect of the mediator, because after all, we're imagining a hypothetical world where we intervene on both of them. Now, this becomes hard if there's an unobserved variable u that affects the value of the mediator m and the outcome y. If this is the case, it's impossible for us to learn about the outcome that wouldn't be realized if the mediator hypothetically took a different value. That's a question that involves potential outcomes defined over the mediator, and you just can't answer it if there's unmeasured confounding of the mediator. This is exactly like how you can't answer causal questions about a treatment effect when there's unmeasured confounding of the treatment. What people often do in practice is they run a regression model where they include the mediator as an additional variable in that regression model. But this is problematic because it opens a backdoor path. The mediator here is a collider. Once you adjust for it, you induce an association between the treatment and that unmeasured confounder u. And so now it's the case that you're comparing a good estimate of the treatment effect to a bad estimate of the controlled direct effect. It's really difficult when people run these regression models and they include extra mediators without thinking carefully about the causal problems they've created by throwing those mediators into the model. So we can solve this problem if we measure the confounders z that affect the value of the mediator. In this case, we can do things that are analogous to what we've done with average causal effects to identify the causal effect of the mediator and also the causal effect of the treatment and how they operate together. So how do we actually identify and estimate controlled direct effects in observational studies? I want to think about a hypothetical example where we're going to think we're that school principal and we want to get kids to read books. Here we're going to focus on estimating the controlled direct effect in a world where we intervene to close the library. So our treatment variable A is whether the librarian visits the class. In our example, this was randomized. So randomly, some students are assigned to have the librarian visit their class and others have the librarian not visit their class. Now, the librarian visiting your class may affect the value of an intermediate confounder, whether you'd like to go visit the library or whether you'd rather go play on the playground. It might be the case that when your librarian visits the class, then you're more likely to want to go visit the library. Now, we might further have subgroups where some kids factually go visit the playground and others go visit the library. So we're imagining a world where we've intervened to randomize the value of the treatment A, but we've let the mediator happen as it happens naturally in the world. So for kids who say they'd rather play, they might visit the playground at higher rates, but maybe some of them change their mind and they decide to visit the library. Finally, we have a potential outcome, the rate at which these kids read books. Here I'm showing the average outcome among many different subgroups of kids. These are the subgroups defined by their treatment condition, their intermediate confounder value, their mediator value. So here we have 2 values of each of those, so there are 8 different subgroups with an average rate of reading books. So this is our data structure. Now we'd like to know, for some subgroups, can we estimate the average potential outcome in a world where we prevent them from visiting the library? Well, let's focus on this subgroup up here for whom the librarian did not visit their class and they told us that they would rather play. Now we've assumed that the only intermediate confounder here is this variable z. And so the potential outcomes by our assumptions under those who visit the playground versus those who visit the library are independent of, the potential outcomes that would be realized if they visited the playground or if they visited the library are independent of the mediator value, whether they factually visited the playground or factually visited the library. Thus, under our causal assumptions in this subgroup, we can take those who visited the playground and use their rate of reading books as an estimator for the rate at which all of these kids would hypothetically have read books if they had been prevented from visiting the library. So here, this is the expected value of a potential outcome under the treatment value 0, because that's the subgroup we're looking at, and the mediator value 0. Now further, this is an average of those potential outcomes taken among those whose intermediate confounder took the value 0. So this is among the untreated with z equals 0. Here is the mean potential outcome under no treatment and prevention from visiting the library. We can likewise take every other subgroup defined by A and Z and make estimates of the average potential outcome in that subgroup. So to summarize just one more of these down here at the bottom, we have the expected value of the outcome if you're assigned to have the librarian visit your class and you are prevented from visiting the library. Here we have the value of that outcome among the subgroup who said that they wanted to go read a book and visit the library, and among the subgroup who said in the intermediate confounder that they would rather play. Now next, we want to aggregate these to an average outcome under treatment and an average outcome under control. So you'll note that the width of these rows is not the same in the A equals 0 and the A equals 1 condition. In fact, in the world where the librarian does not visit your class, there are more kids who would rather play. So this average outcome is more prevalent in that subgroup because A affects Z, and so there's lots of people in this subgroup. Down here, it's more common when the librarian visited your class that you want a book, and so this bottom row is wider than this third row. So what we have here is we can now drop Z, and what we have is a set of people among the untreated, where the distribution of Z is weighted by its factual distribution that's realized when A equals 0. And down here we have a distribution weighted by the factual distribution of Z when A equals 1. And because the causal effect of A on Z is identified here, we have this is the distribution that's realized under no treatment, and this is the distribution realized under treatment. And so we can simply take the simple average of all those predicted outcomes, and we end up with two estimates. We have our estimate of the expected value of the outcome under treatment and prevention from visiting the library, and our outcome under no treatment and prevention from visiting the library. The difference between these potential outcomes is the controlled direct effect, the effect of having the librarian visit your class if we prevent you from visiting the library. Okay, so sometimes we want to estimate with a model instead of estimating non-parametrically. So I'm going to walk through one method of estimating with a model. This method is known as parametric sequential G estimation. And so at a high-level overview, here's how it works. You first estimate the effect of the mediator on the outcome. Here you do that by adjusting for X and for Z. And you also include A in the model as well. Then second, you construct what's called a blipped down outcome. We're going to call this Y tilde. This is the outcome that would be realized if the effect of the mediator were removed. In other words, we're doing that thing where we impute the outcome that a person would have realized if their mediator took the value that we're interested in. So here, our blipped down outcome is the factual value of the outcome minus the difference between the factual value of the outcome as predicted from our model and the expected value of the outcome that would have been realized if the mediator were set to the value of interest, in this case, 0. Next, we estimate a new model, where we now estimate the effect of the treatment on this demediated outcome. So to do that, we model our new blip down outcome Y tilde as a function of X and A, and we proceed to estimate an average causal effect just as we have previously for average causal effects. So to zoom in on these steps a little bit more, our first step is to think about what outcome would have been realized at each value for each person if their mediator took the value little m. And so to do that, we model the outcome Y under the treatment value m by the observed outcome of those whose mediator took the value little m within subgroups defined by X, A, and Z, because after all, that's our sufficient adjustment set. Then our second step was to construct this demediated outcome, where we take our outcome and we subtract off what's called a demediation function. This demediation function is the expected value of Y within a subgroup minus the expected value of Y within that subgroup among those where the mediator takes the value of interest, 0. The demediation function relies on an assumption of no interactions between the intermediate confounder Z and the mediator M. You can allow these interactions in other approaches, but when you exclude the interactions, it simplifies your estimation. So we'll proceed with the simplest case where we assume no z by m interactions. Then finally, the last step is to estimate the average treatment effect on the d-mediated outcome, where we have the potential outcome under some treatment value of interest. If we intervene to set the mediator to the value 0, well, that's just the expected value of our d-mediated outcome among those within the sufficient adjustment set X who have the treatment value little a. And so that's our approach to do parametric sequential G estimation for a controlled direct effect. To conclude, what we've done in this video is we've defined controlled direct effects and we've connected them to longitudinal treatments. By longitudinal treatment, I mean you have a treatment A that affects a mediator M that affects an outcome Y. This is kind of like having two treatments, a treatment A and then another treatment M, that happen longitudinally over time, where the first treatment affects the second treatment. We also built some intuition for a new estimator, which is called sequential G estimation. Perhaps most importantly, I hope you've taken away from this video that mediation involves causal effects not only of the treatment A, but also the causal effect of the mediator M. When asking questions about mediation, it is not as simple as first taking what you did to estimate the effect of the treatment on the outcome, and then adding the mediator M as a new control variable in your regression model. Many social scientists follow that path, but it's really not a good path because it opens up new unblocked paths between A and Y through these intermediate confounders, some of which may be unobserved. Instead, causal mediation proceeds by thinking carefully about potential outcomes, Y, defined under hypothetical interventions to set M to some value and A to some value. These assumptions are stronger than the assumptions required for average causal effects, and we have to think carefully about when they hold and don't hold. When they do hold, then we can proceed with estimation strategies such as parametric sequential G estimation.